Hi, I'm Daniel Pietraita. I'm a robotics software engineer here at Agility Robotics, and today I'm going to talk a little bit about how we incorporate perception into our legged locomotion controller. So I'm going to talk first about our philosophy to tying in perceptive locomotion, and then for the second half of the talk I'll dive into how we actually implement that philosophy on the robot. So core to our beliefs here at Agility are that robots should work in our world, not theirs. This means, they should be able to work with and alongside us in a safe, natural way, ideally performing jobs that are dull, repetitive, and dangerous that humans don't want to do. To be able to do this, they need to be able to seamlessly move through spaces designed for us. The world is designed for humans, and so for robots to be useful in that world, they need to be able to move through this human-centered world. So we believe that for legged robots to be useful and to be deployed in the real world, they need to be able to move through human-centered spaces. So here's a diagram of some potential applications that we're targeting. These are focused on sort of logistics applications, but you can see that even in this sort of classically structured logistics environment, there's plenty of interesting terrain for the robot to have to tackle. So you can see on the left here, there's this inspection task, potential inspection task where the robot might need to walk up and down a flight of stairs or walk over curbs or parking curbs and things like that. There's also this sort of trailer load and unload task where the robot might need to get in and out of a trailer. There's also plenty of places in warehouses where the environment is just really tight and constrained and cluttered. So for some of these sort, carry, and fetch type tasks, the robot needs to be able to walk through these kind of constrained hallways with shelving and things in the way. So these are all interesting types of terrains, even in a traditionally sort of more simple environment. So we want our robots to be able to move through all these interesting terrains. So traditionally, legged locomotion research has focused on building robust blind controllers, and our company is no different. Digit, our current product, has ancestry that goes back to Atrius, which was a research robot at Oregon State University. This robot had no visual perception. It could only sense the world through force interaction with its legs. And you can see that there was a lot of work done on building sort of compliant, physics-first based locomotion controllers that can react to all these smaller step obstacles really smoothly without any visual perception at all. So, this extended to Cassie, which was our first product at Agility Robotics that we sold. Cassie also had no visual sensing, but could do a similar thing in a nice integrated package where it could walk through these, small step obstacles really robustly, which is pretty remarkable if you think about the fact that the robot can't see anything that's going on here. But obviously, blind controllers can't do it all. So eventually, basically, the environment gets complicated or constrained enough that blind locomotion just doesn't cut it. One of the classic examples of that is stairs. So stairs are hard. They're very constrained where you can place your feet, and there's a lot of elevation change happening really quickly. As anybody who's tried to walk down or up a flight of stairs with your eyes closed can attest to, it's pretty hard to do this, especially if you aren't expecting there to be a flight of stairs there. So this is one example, but there's plenty of cases where blind locomotion just isn't enough. So to tackle those types of more interesting terrains that you might find in the real world, we need to integrate visual perception, and this can unlock new capabilities. So, here's just our Digit robot with a full sensor suite, able to really smoothly tackle this this small flight of stairs in the lab. But integrating visual perception does unlock new capabilities, but it also introduces new sensitivities into your locomotion stack. Now you have like a new set of inputs that your locomotion controller is responding to, and perception data can notoriously be quite noisy. It can be unreliable, or it can be lacking context. So, on the left here you can see this is just a clip from one of our stereo cameras that we use here on Digit. It's pointing at a flat ground, so it does capture roughly the fact that the ground is flat, but you can see there's all this undulating waves and noise that can be even up to a few centimeters of noise in this type of data. In this data, if it's being put into your locomotion controller, you have to be able to deal with the fact that it might be noisy like that. Also, cameras, they have their own sets of failure modes, so some common problems are maybe moisture on the lens or lens flare. These can cause kind of unreliable data integrity. And then, these sensors can give technically the correct data, but that data can just be lacking context, like maybe vision isn't enough. So, for example, here, the same stereo cameras are showing a sidewalk into some tall grass, and the point cloud captured is, you can see that it is capturing the fact that there is tall grass there, but what it's not capturing is the fact that there are actually some potholes under this grass created by groundhogs or something like that. So sometimes visual information can be correct, but not enough. Basically, we don't want to, it's not enough to just rely on it alone. So we believe that a really robust underlying blind locomotion controller is important to be able to handle these types of corner cases where perception fails. And there's some evidence to suggest that nature does something like this. So the biomechanics community might call this something like reflexes. But yeah, here's a clip from Monica Daly's lab showing a guinea fowl running across this hallway, and there's this tissue paper hiding the fact that there's this dip or this hole in its path. So basically tricking the perception system to fail, but the guinea fowl is able to really smoothly recover from that disturbance, that unanticipated disturbance. You can just watch that again. It's pretty cool to see how smoothly it can react to a disturbance that it didn't know was there, just due to the fact that the perception system was basically lacking the full context of the scene. So we want to mimic as much of the cool things we can find in nature as possible. So, here's the same lab setup with Digit, and you can see, we're tricking the perception system in the same way, and it is able to respond to that disturbance in a really smooth way without really any hiccups at all, which is pretty cool. We're pretty proud of a lot of work went into getting our blind locomotion control to be compliant enough and understanding the physics well enough that we can do these types of behaviors really smoothly. So we're pretty proud of that fact. You can kind of see here the foot lands on the tissue paper, that's where it thinks the ground is, and then just pushes right through, and there's a slight dip to the center of mass, but other than that, pretty much just walks right through, which is pretty cool. So, those two previous slides showed some examples that were obviously pretty contrived, that would only be found in a lab, but there's plenty of places in the real world where you can have kind of similar behavior. Here's, example of two digits climbing this hill. So, perception is enabling the fact that we can climb this hill smoothly, but this grass is hiding all sorts of potholes, like I kind of showed before. So if you watch the digit on the left here, it steps into this grass, kind of slips into a pothole, and the underlying robust controller is able to basically handle that case where perception was incorrect or giving the wrong context. And as you watch these digits climb this hill, there's a bunch of other potholes they're stepping into, and although perception is helping us climb this hill, we're also relying a lot on the robustness of our underlying controller to get us through those small hiccups. So that's kind of core to our belief is that, in order to deploy, bipedal robots in the real world, you really want to build locomotion capability on top of a foundation of robust blind locomotion. So you can't just rely on perception alone, basically. So now that I've talked a little bit about our philosophy, I'm going to go into more details about how we implement that philosophy on Digit. So to start, you obviously need to give Digit the ability to sense its surroundings, and it has a sensor suite informed by 3 generations of robot products that we have here. So our first product, Cassie, as I said before, had no visual perception. That was primarily an R&D robot sold to universities. But going forward with Digit, we wanted to produce, a bipedal robot that could actually do useful tasks in the real world. So we went through a couple iterations of Digit internally before the first Digit product that we sold, which is our internal Digit V3. As we were progressing through these iterations, we were realizing how important it was to incorporate perception into not only locomotion but also manipulation to do useful applications. So you can see we just kept adding more sensors basically, and then we're continually iterating. So the next version of the robot will have even more sensors with more optimal sensor coverage, better data quality, and hopefully better reliability as well. The current Digit that we sell has a pretty good sensor suite. So it has a long-range LiDAR on top that enables localization, mapping, and longer-range obstacle detection. But then on its chest it has a stereo camera plus color camera module sort of pointing down that enables perceptive manipulation. Then a forward-facing high-resolution color camera for easy teleoperation. And then it has these 3 stereo cameras in its pelvis which provide detailed terrain information and close-range obstacle detection. And this is primarily what we use to build a representation that we can tie into our locomotion. So, Digit has all those sensors, but then it needs to fuse information from all those sensing technologies to build a single coherent model of the world. And so here's a video of basically Digit in the lab, just kind of walking around these little structures. You can see on the right, that's basically what Digit is interpreting of the world, how it sees the world. So you can see there's this green or colored patch. That's basically it's building kind of a local elevation grid that's showing the height of the terrain just around it. Then it has these black cells. So black cells are areas that the robot has decided are obstacles or places that it shouldn't navigate at all. So you can see it thinks that this stack of boxes or wooden pallets is basically too tall and it shouldn't try to step up on that. So it's labeling it as an obstacle. But then as it comes over to the other side and looks at these steps here, it's those are small enough steps that it realizes that it's fine for it to step up on that, so they're not labeled as an obstacle. But you can see that the edges of these steps are labeled as kind of red cells. These red cells basically signify that that's somewhere that the robot shouldn't place its foot, so it's like an unstepped footstep location. So obviously you don't want to step directly on the edge of a curb because you could slip or trip, different things like that. So it's realizing that it can step up on these steps, but it shouldn't place its feet right on the edges. And then in the background it can see this wall as an obstacle. And all this is happening really fast. So this is updating at 10 hertz, incorporating information from all of our sensors, so it can respond to new things happening in the environment. So here I am walking into the scene. It's tracking me as I'm walking into the scene as an obstacle, and I place this box down, and that box is tall enough that it realizes that, okay, yeah, this is an actual obstacle. I probably shouldn't step up on that, so it labels that as black cells. So yeah, that's kind of the representation part, but how do we actually build a controller around that? So as I said before, you really want to start with a foundation of compliant, dynamically stable blind locomotion. Really, I don't think there's any amount of work that's too much work to focus on here. So you could just keep making it more and more robust, and it will just improve your whole system. And we've spent a lot of work here at Agility on our blind controller. And we're pretty proud of the fact that this is digit with all of the perception system disabled. It's able to accommodate like these weird, the terrain changing compliance with this foam, these 2x4s which are jumping all over the place. This little step up here, and it's able to just kind of walk through it without any problems, without really any hiccups at all. Which, we're pretty proud of our blind control here at Agility for sure. But one of the places that we first noticed that this robust blind controller can have issues is when disturbances are continuous, and especially continuously pushing in the same direction, which happens anytime you're ascending or descending a hill. So this is just digit in a simulation environment, walking up a hill with just our blind locomotion control. You can see here it is successfully climbing the hill, but it's stubbing its toe every time because it doesn't know that the hill is there, and it just doesn't look great, which when you're trying to deploy robots in the real world, aesthetics are actually important. But more importantly, when it's going back down this hill, not only does it not look great, but it actually is a large enough disturbance that it actually completely falls over, which obviously we don't want. So what we do basically is we have our optimization-based locomotion planner, and we add some constraints to that that basically say that the planned footsteps need to respect the terrain height at those footstep locations as well as the terrain slope at those footstep locations. So pretty simple equality constraints, but just adding those simple constraints can, here on the way up, it looks way nicer. It's like smoothly and quickly walking up the hill without any foot stubbing, and then more importantly, on the way back down, it's able to successfully and smoothly climb down this hill without falling over like you saw before. So yeah, obviously simulation is one thing, but we want to make sure that matches reality. So here is a video of a robot operator just driving the robot straight up this wooden hill, just by pressing forward on a joystick basically, and then all the underlying locomotion is handled autonomously. So you can see it, and then on the right is kind of what it's seeing and what it's planning. So here it's flat ground, it's planning just kind of flat locomotion, and then here I can see the hill kind of coming in front of it, and you can see it's kind of accommodating that hill into its gait. So the planned footsteps are now matching the slope and the height of that hill, and that allows us to smoothly walk up this hill with on hardware as well. Just play that one more time because it happens pretty fast, but yeah. So yeah, that terrain matching, kind of the feet matching the terrain, it helps a lot, and it allowed us to climb all sorts of hills and descend all sorts of hills inside and outside. But locomotion, we noticed basically that we could still fail when the robot placed its foot in an unsafe foot location. So one immediate example of that is just the edge of a curb. You don't want to step directly on the edge of the curb. You can trip or slip, which can lead to a fall. So here's just an example of, so the previous terrain matching constraints are enabled, but that's it. So you can see the planned footsteps are respecting kind of the height of the terrain around them, but there's nothing telling it that it shouldn't place its foot right on that edge. And as you can see here, what can happen is, if you are unlucky and you step right on the edge, then you start slipping and sliding, and it can recover for a little while, but especially on taller curbs, that can pretty much always lead to a fall. So we obviously don't want that. So we add another set of constraints. These are soft constraints that basically pull the planned footsteps away from any areas that it deems unsafe. So here, this curb edge is sort of an unsafe step location, as we just saw. So, we add constraints pulling the planned footstep locations away from that area, and you get this kind of nice footstep plan that now is completely avoiding, the curb edge, which lets it smoothly climb over the curb or step up onto the curb without slipping or tripping on that curb. And we can go up and down and back and forth on this. So this is just showing that thing that just caused the robot to fall, just with a couple additional constraints, is now something that the robot can easily handle. So yeah, like before, simulation's one thing, but hardware is another. But with the same set of constraints, but now instead of our perfect simulation environment, we're building this local map representation and using that to plan over instead. So you can see, same thing, we have a robot operator like driving the robot around in circles. We're just testing this capability out. We have this kind of log in the way that can trip it, and then in the back just like a couple curb steps that it has to go up and down. You can see on the right, the robot is, it can see the log there, and then these red cells on the edge of the log are saying, okay, don't place my feet there. And then it can plan this footstep plan that goes over the log instead of through it. So you can watch it just kind of steps nicely over the log, and then we're driving it around to the other side, and it's able to really easily and smoothly climb up and down. Same thing on the other side. The edges of the curbs are red because it shouldn't place its feet there, and then it's using the elevation to climb up and down smoothly. So that's the kind of thing that it looks really easy when the robot does it now, which is really what we want, because it should be easy for the robot to do this. And the robot operator doesn't have to think about it. He or she can just drive the robot over these curbs, and it should just be able to handle all the locomotion on its own. So and then here again at the end, just stepping over that same log. So we just went around a lot of times, but for the sake of time, I'll move on. So yeah, adding those constraints that allow the robot's feet to match the slope and height of the terrain, as well as keep the feet outside of kind of unsafe footstep locations, really improve our locomotion capabilities a lot. But then there are some places that digits should not locomote through at all. And it's pretty obvious to say, but things like walls or people, the robot shouldn't try to step through. So if we, in simulation, just tell the robot, go to this other room to grab a package, and we don't have obstacle avoidance on, it'll just walk straight there and slam into a wall and fall over, which is not ideal behavior. Especially, we would never want that to happen in real life. We have that to build upon our kind of like perceptive locomotion. We also have some high-level planners that take into account obstacle information and build obstacle-free paths and trajectories through the world. So this is that same API call, which is basically like go to that other room to grab the package in simulation, and here incorporating obstacle information, it's able to smoothly plan a path and follow that path with a trajectory, and then the locomotion's kind of tracking that trajectory and able to nicely navigate into that other room without any collisions or falling or anything like that, which is nice. So that's not only in simulation, that also works on hardware, and not only does it work on static obstacles, but also dynamic obstacles. So here the task is pretty much the API call is something like go over there, go grab that tote on the other side of the work cell. So Digit initially thinks that, or it sees that there is a person here, but the path to the tote is clear, so it plans a straight path to the tote. But then as the person sort of gets in its way, doing his own task, Digit is able to quickly replan a an obstacle-free path to the tote and successfully complete its task. So this is cool because it just shows like, you know, how fast, you know, the humans incorporate, or the person's being tracked with our local world representation, and then you know, the path and trajectory are replanned, and we're able to locomote in a safe way through this environment. Yeah, so that's kind of like the different layers of our perceptive locomotion stack. And when you put it all together, it allows Digit to smoothly traverse a wide spectrum of not only complicated, but also, you know, dynamically changing environments. So, you know, here's a couple examples of the environment changing really quickly in front of Digit, and Digit's able to autonomously handle that. Here's another cool one. So Digit's basically just told to, you know, go to a waypoint straight ahead of it, in front of this box to the left. And then a sadistic controls engineer pushes this cart in front of it, and it has to accommodate that cart in its gate and step over it really quickly. I think this just shows how fast everything's happening. So, you know, the cart's being pushed, it has to incorporate that cart into its local world representation, change its gate, locomotion gate accordingly, and then actually track that gate with controls all in, you know, a very short time span. So we have a really, you know, strong focus on performance, you know, here at Agility. This clip I thought was cool because it just shows that, you know, this constraint setup that we put together, it generalizes to other gates, not just our normal walking gates. So here's kind of an experimental hopping gate that some of our controls engineers have put together. And with those same set of constraints, you can now hop over this curb instead of walking over it. So not necessarily a very useful gate, but you know, we like having fun here at Agility too. So yeah, it's pretty cool, I think. We also like to push our system to its limits. So here's another just sort of obstacle course that some controls engineers put together. We have an operator manually driving the robot through this course. They're just giving joystick commands, basically like go there. So the operator is just having it go up and down the steps and forward and backwards, and the robot is autonomously handling all the terrain with its locomotion stack. So, you know, you can see there it went up, you know, a single curb, which is like 15 centimeters, and then a double curb, 30 centimeter step up, and then here the operator has it go backwards down this half a meter step down, which is pretty cool. It's able to handle that pretty smoothly, drives it over this kind of trip obstacle. You can see here it actually does kind of clip a little. Just, you know, those little inaccuracies in perception can mean this can happen, but as you can see, the robust underlying controller handles it fine. And then, as you saw before, just, you know, driving up this kind of wooden ramp here. So, you know, another just kind of fun seeing what our system is capable kind of test. Obviously, hopefully, or probably we won't encounter anything exactly like this in the real world, but we like to test our system to the limits as much as we can. So here's some more clips. This is just, you know, that stuff doesn't only work inside, but also outside. So here's somebody driving it around a parking lot, and it's able to kind of, you know, we're going at these curbs kind of off angle, and it's able to smoothly step up and down on these parking lot curbs. So, you know, nothing changes about our locomotion stack. All the same constraints and perception apply, but it's able to handle stuff outside as well. Here it is kind of stepping up on a curb, then transitioning into this kind of unstructured hill, muddy hill, and then back to this more like structured curb. And it's able to transition through those different types of environments without any changes to the locomotion stack, which is pretty nice. Now that we've added all these capabilities, we've been having fun going out to some local trail networks and just hiking it around on trails. So here's it climbing, you know, another pretty muddy hill. It's able to do that successfully. Here we are in Bend, Oregon, climbing it up a fairly steep, the footage never does it justice, but fairly steep hill covered in, you know, thick dust, sand, little rock pebbles, all sorts of stuff that it needs to be able to deal with. And, you know, perception's helping it climb up this steep hill with those constraints I mentioned before, but then perception can't really pick up on all these tiny things going on, like the sand and these little pebbles. So that's where our robust blind locomotion is helping us out a lot. You can see we can pretty smoothly tackle this pretty rugged terrain without any problems. That's pretty cool. Here's another, just going downhill near our old office, so with some mud, pretty smooth. This one's cool. This clip is cool because first it needs to step over this log and then climb the hill. Because the operator decided they were going to drive it straight over the log for fun, probably. Oh, whoops. And yeah, it's able to handle that, pretty gracefully. So it steps over the log and then climbs this hill here without any problems. Here's another, just bigger log. So same kind of behavior though. Step over the log and keep going. So this is just showing all of our constraints working together, the terrain matching and the avoiding unsafe footstep locations. So having all that locomotion capability is great and all, but really what it enables our customers or our applications developers to focus on their application problems and not have to worry, so that they don't have to worry about kind of the details of how to get through the world. So this is a toy application. There's no usefulness to this, but there's a toy application that we put together just with a few lines of code. You can basically command the robot to follow GPS waypoints, and here we have it. We place GPS waypoints in the shape of our Agility Robotics logo on the hill right outside of our office. And so with just a few lines of code, you can have the robot kind of autonomously track these GPS waypoints and is dealing with the hill, the grass, these potholes. All that is dealt with by the locomotion stack, and the API is really simple, high-level descriptions of what you want the robot to do. So this is just a toy application, but you can imagine using similar API calls to have autonomous facility inspection or any other types of applications like that, where the developers don't want to have to worry about exactly how the robot's placing its feet or how the robot is navigating through the world. They just want to worry about the application itself. And then here is some initial applications that we're targeting right now, which are primarily logistical in nature. So in these logistics environments, there's use cases where the robot needs to grab totes and boxes and kind of move them through the space. Same thing where the applications engineer just wants to think about how the boxes are, where to move the boxes and which boxes to move, things like that. But then the robot should be able to handle all the navigation, locomotion, and manipulation on its own. So, there's also perceptive manipulation happening here, which honestly could have its own talk. There's plenty of details and complications there. But this is just showing also off some of the locomotion where it's having to navigate around this human, which is in the same work cell. And then, that's what's cool. It doesn't only apply to people, it can also apply to other digits or any other robot. Just this egocentric, intelligent navigation means it can navigate around this. These digits don't know that the other thing in their path is another digit. They just see an obstacle that they need to get around, and this just means that our operations can scale pretty easily without adding a lot more complexity. So, here's a clip showing that. This is now 4 digits in the work cell, and they're able to all kind of avoid each other and move through the space and grab and place totes just using this kind of egocentric navigation that I've talked about. So I think that's the end of my talk. So I'll end on a note of just mentioning that we are hiring. We're growing super fast here at Agility. There's lots of really hard, challenging, exciting problems that we're tackling in order to put these bipedal robots out in the real world doing useful things. So if anybody's interested in pursuing that mission with us, we'd love for you to apply at agilityrobotics.com/careers. And I just wanted to say thank you to the workshop organizers for inviting Agility Robotics and myself to talk. And yeah, have a nice day.